Hi, this is George Diamond. Now today we're going to be looking at the definite integral as a function of x. Here, let me put my box of goldfish crackers down and we'll go ahead and get started with our video. Now in our textbook, this is section 4.4. We're looking at the fundamental theorem of calculus. The first part of the fundamental theorem of calculus and then part 2. This video here hopefully will lead us into the second part of the fundamental theorem of calculus. That will be our next video. But this video here, we need to take a look at what we mean by a definite integral as a function of x. Now these are kind of strange because these are functions in which part of the function is a definite integral in which the upper bound of the definite integral is a variable. Now the lower bound is a constant and the upper bound is going to be a variable of some type. So when you think about this, this is a capital F of x as you look at our function. So capital F of x is equal to the definite integral from a to x, f of t dt. Now, one thing about these types of functions, the integrand is described in terms of t. The upper bound is described in terms of x. So they're going to use two different variables for the upper bound and the integrand. So typically, the integrand is described in terms of t, but not always. It could be an angle or something like this. But keep in mind, the integrand and the upper bound are going to be two different variables. Because remember, the function itself, f is actually a function of x, not t. Right? And the lower bound is going to be a constant. Right? So when you think about this, as you look at this function, this is what the function describes. Right? The independent variable or function is described as the upper bound of your integral. So the independent variable is x. Okay, that's the upper bound of our integral. Okay, the dependent variable is going to describe the accumulated area from a to x. So the area under a curve from a to some variable now. So some variable. So some variable x. All right, so the a to x. So once again, this is a type of function in which the independent variable is the upper bound of your integral. The dependent variable is the accumulated area under the curve from a to x. So these types of functions, there's several applications. One of them involves something called accumulation functions. We'll be looking at those in a later video. But let's start off. Let's see if we can evaluate a couple of these types of integrals. We'll do a couple of them. They're really not that difficult. You still got to find your antiderivative. You have to substitute your upper bound minus your lower bound. So you're going to evaluate this type of definite integral just like you would, except the upper bound is a variable. So our answer is going to be in terms of x. It's not going to be a number like some of our definite integrals we looked at before. So let me erase this and let's get started with our first example. Okay, let's see if we can evaluate one of these definite integrals now in terms of x. Get this erased. All right, now let's see. For our directions, let's say we're going to find f as a function of x. All right, so find capital F as a function of x. So as a function of x, and evaluate it. Okay, and evaluate. All right, so evaluate. Evaluate the function at x equals 2, x equals 5, and x equals 8. So we're going to evaluate a couple of function values. All right. So let's get started with our first problem now. So our first problem. Let's say we've got this particular function. So problem number 1, we've got capital F of x is equal to the integral from 2 to x. And you see that integral now. This would be the accumulated area from 2 to some number. So from 2 to x of this cubic polynomial. So this will be t cubed. So t cubed plus 2t. Minus 2 dt. So this is this is going to be our definite integral in terms of x. so as a function of x. So once again, f of x is our upper bound. F of x represents the accumulated area under the curve from 2 to some number. Right. So let's get started. Let's say we've got, so first thing we want to do is find our antiderivative. So let's get our antiderivative in terms of t, and then we've got to substitute the upper bound minus the lower bound. So we need to evaluate this definite integral here. Right? So as we evaluate this, and the antiderivative of t cubed would be t to the 4th power divided by 4, okay, plus the antiderivative of 2t, remember you're just adding 1 to your exponent divided by the exponent plus 1, so the antiderivative of 2t would be 2 times t squared over 2 minus 2t from 2 to x. Now what happens as you simplify here, the 2's are going to cancel out, so we'll just cross those out. Okay, and now let's finish our definite integral. We have to substitute the upper bound minus the lower bound. So we're going to take the x and substitute in for every t now. And then we're going to substitute the 2 in for every t, just like you would in a definite integral that we've been working with before, in which the upper and lower bounds are both numbers. Substitute the upper bound minus the lower bound. Now, so as we evaluate this now, this will evaluate as so actually x to the 4th power, or 1/4 x to the 4th, okay, plus x squared minus 2x. Okay, that's our upper bound. Okay, minus, now let's substitute 2 in for t now. So this will be 1/4 times 2 to the 4th power minus plus 2 to the 2nd power minus 2 times 2. Okay. Now, simplifying this now our answer, like I said, is going to be in terms of x. We're not going to get just a number, like the area under the curve, so just a number. We're going to get our function in terms of x. So now this will simplify then as 1/4 x to the 4th plus x squared minus 2x. Now this here would be, this will be 4 minus 4. These here would add up to 0. Now 2 to the 4th power, 2 to the 4th power would be 16, so this would be 16 over 4, or 4, so it would be minus 4. All right. Now this is f of x is equal to this function now. So once we have evaluated the definite integral, substitute the upper bound minus the lower bound, we get this function now. So let's start off. Now first thing we want to find is the function at 2. So let's get f of 2 first. This would be 1/4 times 2 to the 4th plus 2 squared minus 2 times 2 minus 4. And let's see, now this is 0. This will be 2. So let's see, this will be 4. That'll be 4. Okay, minus 4 here would be 8. This is 1/4 here, so it would be 1/4, not 1/2. So it would be 1/4 times 2 to the 4th power. So 2 to the 4th power would be 16. So this will end up as what? 4 plus 4 minus 4 minus 4, which is 0. All right. So the function at 2 would be 0. Now think about this now. When we substitute 2 into our function, okay, think about the integral up here. So we're integrating from 2 to 2. So remember we said in one of our previous videos, anytime you're finding an integral in which the upper bound and the lower bound are the same, right? The area under the curve is 0. So the area under the curve from 2 to 2 is 0. And this is what you see right here. So by substituting the 4 in, get your function at 2. This is the area under the curve from 2 to 2 of any function is going to be 0. All right. So I just wanted to point that out. Okay, let's get, so this was 0. Let's try another one. Okay, let's do the function at x equal 5, right? So this would be f of 5 is going to equal 1/4 times 5 squared plus 5 to the 4th power, rather. So 5 to the 4th power. Okay, plus 5 squared minus, let's see, minus 5, say plus 5 squared minus 2 times 5 minus 4. Now let's see, I did this on my calculator earlier. This is 167.25. And up here with 167.25. Okay, so this will be the function at 5, right? This, now keep in mind, when you think about this, now this is the accumulated area between the curve and the x-axis from 2 to 5. So this is what we're getting now. When you see 167.25, and we substitute this in, you're getting the area between the curve and the x-axis from 2 to 5. Okay, let's try one more to look at. This is the function at 8. So f of 8 would be 1/4 times 8 to the 4th plus 8 rather. So 8 squared minus 2 times 8 minus 4. And I've done this already. This is 1,068. So 1,068. Now keep in mind when we evaluate 1,068, okay, x is 8. This is the point at 8, 1,068. So that would be an actual point on the curve of this function. So if you can imagine the curve of that function, that'd be one point on that curve. Would be at point 8, 1,068. Okay. This is problem number 1. Let's do one more example. Now I'm going to use the same x values again. So we'll let x be 2, x be 5, and x be 8. Let's try a different function this time. So we'll use a different function. So let's erase this. Now this is, as you look at these two examples, this is a couple examples that I picked out of our textbook. Now we're using a Larson textbook, so I just picked a couple of homework problems that we're going to run through them. Okay, let's take one more problem. Let's try a trig problem. All right, so let's take so problem number 2. Okay, let's say f of x is equal to, okay, the integral from 0 to x of let's do sine theta. So sine theta d theta. Okay, so instead of t, we're using theta. Now, keep in mind this will be the accumulated area between the curve and the x-axis from 0 to x of sine theta d theta. Now, first thing we want to do, let's get our antiderivative. Now, the antiderivative of sine is negative cosine, so this will be negative cosine theta from 0 to x. So find your antiderivative. Now, to finish evaluating our integral, we got to substitute the upper bound minus the lower bound now. So this will evaluate as negative cosine x minus negative cosine 0. All right? So negative cosine 0. Now remember, now on your unit circle, this is our unit circle. Okay, 0 is here. Okay, that's the point 0, 1. The x value is cosine, the y value is sine. So actually this is 1, 0. I'm sorry, let me try that again. So 0. So cosine 0 would be, so x equals 0 would be, so this would be 1, 0. So 1, 0 here. So this is cosine, this is sine. So cosine would be 1. So we end up here with negative cosine x minus a negative 1, or negative cosine x plus 1. Okay, now this is f of x is equal to negative cosine x plus 1. Right. Now let's try our function values in this expression, in this function here. Right, so f of x, so this would be f of 2 is equal to negative cosine 2 plus 1. Now I did this on my calculator earlier, I get 1.416. Okay, let's do the function at 5. It'll be negative cosine 5 plus 1 is equal to 0.716, so 0.716, and we did one more. So the function at 8 is negative cosine 8 plus 1, and this time we get 1 point. Well, I'll let you do the last one here, right? So we'll do the last one. I didn't do it on if you have a calculator, you can punch that up on your own. Okay. Hopefully you found these two examples helpful. Right? So if you have to evaluate this type of definite integral in which your integral is actually part of a function in which the upper bound of your integral is a variable, okay, this is how you would do it. Right? And hopefully you found these two examples helpful.